Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today, as with most of my screencasts, I will be discussing the reciprocal system, specifically the reciprocal system Microcosmos database. You can see the two main menus here. This left panel is for the Microcosmos database, and the right panel here is for the Macrocosmos database. I've already covered all of the layouts in the Macrocosmos database, and I've covered many of the Microcosmos database layouts here. We have one more to go for liquid vapor gas matter properties, and that's electrical and thermal conductivity. So let's click that. Takes a couple seconds to load in. We're going to stick with water as our sample molecule. You can see that I have 1,344 records in the system, so I've covered all the elements and many compounds, enough to verify the system. If the compound that you're interested in is not in the system, you can simply add it in. You just click New, and you fill in all the data. So let's go here. As usual, we have the element compound or mix symbol H2O here, of course, because that's what we're working with currently. Ice, water, and steam. Form number 1, atomic molecular weight, observed melting temperature, the vapor gas symbol. Sometimes it's different, so if it's different for a vapor or gas, you'd put that here. Atomic molecular weight for the gas or vapor. The critical temperature calculated and observed is here. See, they're pretty close, not exact, but pretty close. Now, we use Carl Yaw's work, which is the Chemical Properties Handbook, as our comparison with the empirical data. So here, for the thermal conductivity regression coefficients, we have A, B, C, and these are for SI units. So that therefore we can compare our theoretical calculations to the empirical ones. But you have to consider the empirical ones are actually approximations. We're not comparing to actual data, just a good approximation of them. Okay, so you input the temperature here. This is in this rectangular box, so you know that's an input. 600 K. All the temperatures that we have in the system are in Kelvin. So calculate electrical resistivity in ohm centimeters here. Electrical conductivity, which is obviously the inverse ohm, inverse centimeter. Electrical resistivity for thermal resistance, which can be different, by the way, and you can see that it is ohm per centimeter. Electron-specific heat, that's in volts per Kelvin. It's very interesting. Thermal resistivity is calculated here. Thermal conductivity is calculated here, and then we compare it to the Yaw's calculations. So you can see the Yaw's calculation and the reciprocal system calculation is quite close. Now, if you use this other approximation, which is Sato-Rydell, it's pretty much off. So just keep that in mind. I just threw in this is from Reed, page 550. Which I think it was originally Sherwood and Reed from that book. Works best around boiling point. Be sure to have entered the boiling point on the previous screen now. Yeah, and obviously this is way off from the boiling point. For this compound, there's no electrode reactions and electrode potential. There's nothing here. Let's see. Let's read the tooltip. Neither conventional theory nor the reciprocal system have a method to calculate this, so the observed value is under 0. One source is the structure and properties of material volume 2 by Britaffi et al. So, this is just as another property to put into the system. All right, so this is the liquid. So now let's go look at the vapor and real or ideal gas calculations. Again, we have the box here. That's temperature K 646.65. And we look at the Yaws thermal conductivity regression coefficients for this, which is interesting. And we calculate thermal conductivity. So I get 4.82678 times 10 to the minus fourth versus Yaws, which is 5.17027 times 10 to the minus. You know, it's not too bad in terms of closeness. Let's see, let's look at this tooltip here. Extensive research has been done on gas thermal conductivity in the reciprocal system, but given that the Maxwell, let's look at this. The Maxwell distribution is accepted, let's look at this. The estimate is probably close to the ultimate result, and that will be used here until the exact equation can be found. So, okay, so that's this UCAN estimate. Okay, so all right, that's fine. All right, and let's just look at a few of the properties, specifically the index of refraction. So the liquid, vapor, temperature, and real gas. And so you enter in the pressure that you want, say 500 atmospheres here for the liquid, 20 for the vapor, and 500 for the real gas. And then we calculate the density, and we calculate the index of refraction. And this is an extra calculation for the refraction constants. Let's just see, yeah. Click the button to change the default values. You probably shouldn't have to change that. Temperature, thermal distribution of elements, stars, well, it's not. This box is only for elements. Okay. And of course, the notes are the same as before. I should be able to go down. Okay. Yeah, same. All right. So that's pretty easy today. We covered thermal conductivity, resistivity, electrical resistivity, and conductivity. And we compared it to the Oz value here. And then we did the same for the vapor and real gas calculation. And of course, the index of refraction. Okay, well, that was pretty quick. I'm going to close this up. So we've now covered all the liquid, vapor, gas, matter properties. So study the reciprocal system and prove it for yourself. The simplest possible treatment of the theory is my original work, published way back in 1971, called The Unmysterious Universe. It has all the concepts, many, many illustrations. It's still the best introduction to the theory that there is out there. I left the mathematics out. That work focuses almost entirely on the concepts. Once you understand the concepts of the theory, then you can go on to the mathematics, which I give in great, great detail in my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file, 711 slides in the PowerPoint file, thousands and thousands of equations, diagrams, tables, figures, everything. It'll take you months to go through that work. Then, once you've done that, then you can understand these two database modules much better, where the equations for the calculations come from. So in the Microcosmos database here, I've covered solid matter properties, including interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes and atomic spectra. I've covered liquid, vapor, and gas matter properties, volume and density, specific heat, energy and entropy, viscosity and surface tension. And today I covered electrical and thermal conductivity. This database module also covers the cosmic elements and subatomic particles, including both material and cosmic. The cosmic sector is the inverse of our material sector. So there are two halves to the physical realm, our material sector and the inverse or cosmic sector. In our sector, velocity is s over t. In the inverse sector, velocity is t over s. Space and time are reciprocally related in motion. So the reciprocal system is a supersymmetrical theory of space and time. It completely and utterly supersedes all other theories in modern physics. Now, in the right panel here, you see the Macrocosmos database. Here I cover all the astronomical properties for the universe as a whole. Galaxy clusters and groups. Galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas, and dust, and voids. And events here, if you want to go right over to the videos or pictures of any of these objects, astronomical objects. Both of these models contain excellent graphing routines as well. Now, my theoretical physics mentor, Julie B. Larson, was also a theoretical economist, and I've made his work in economics also fully computational. As optimal economist, and implementation of Larsonian econophysics completely supersedes Keynesian economics. It covers the microeconomics of individuals, businesses, and business sectors, and the macroeconomics of whole countries and regions. There's nothing like it in the world. And if you want to learn more about that, you can find my free paper on the web called Theory of Microeconomics and Macroeconomics, Larsonian Econophysics. It's a PDF, and you should carefully study that paper. You'll understand economics better than anybody else once you grasp everything in the paper, and then you can get the computer program. All right, so that's it. Please study the reciprocal system and prove it for yourself, and thanks for your attention.